Hopefully you managed to get somewhere with that activity and create those two graphs. You may have set up your scale slightly different. If you're creating a graph of something, it helps to spread the scale out as much as possible. Some of you might have graphs that you didn't spread it out as much as possible, and so your time might be, you might have crunched it up like this and made it smaller or whatever, something like that. It's best to try and spread it out, or you might have it shorter or something. It's best to try and spread it out as much as possible so you use up the whole grid. I didn't make this go probably high enough for what it's going to be by 8 minutes, but I wanted to keep the scale similar to the other graph. The big difference between these two graphs is this one's going up, whereas the other one is going down here, right? Can we? You have lots of time after to work on helping people, but best if you either work by yourself or listen, okay? Yes? Anyways, the big difference is one's going down, one's going up, right? The two different situations. The second one here is the water's being drained, right? Water's being drained at a rate of 0.5 liters per minute. The slope of this, if you actually calculated the slope of this, the slope in this situation is negative 0.5 liters per minute. It's the rate that it's being drained at. Right? If you calculated the slope of this and you counted, right? If you went from one point to another, it goes down 1 liter for every 2 liters across, or it goes down a half liter for every 1 minute, right? 1 minute minus 0.5 liters. Minus 0.5 liters per minute, that's the slope. It's going down, right? Whereas the first graph is going up, right? For every 1 minute, it goes up 1.5, plus 1.5 liters. Okay, the slope here is plus 1.5 liters per minute. The rate that it's being filled or drained at is the slope, right? This is the slope. The slope's the rate of change. Okay, so that's one thing to notice. One goes up, one goes down. The other thing is it talks about, what do the intercepts represent here? The intercepts, what do the intercepts represent? Here's one intercept, here's another intercept. That's the not the X-intercept, that's called the Y-intercept. In this case, actually, it would be called the A-intercept. I'm going to call it the Y-intercept here so we don't get confused. The vertical intercept, you could call it the vertical intercept. They might talk about that. Or you might talk about the A-intercept because that's the variable here. Either one of those things, right? What does that represent in this situation? In this situation, it's 4 liters here. What does that represent? In the table, it's right here, right? There's the 4 liters. What does that represent? The amount of water when? Amount of water at the start, right? I'm going to put at time equals 0, i.e. at the start. Okay, at time equals 0. In any situation for any linear function, the y-intercept is going to represent the starting value. Intuitively, you know this already, right? If I showed you any graph and said, if we drew some kind of a graph here, whatever it is, I guess I could draw it on here. Whatever graph you happen to draw, wherever it crosses that y-axis, right? If we make some kind of a graph here and we say starts here and goes there, whatever this value is, that's the starting value at 0, wherever it starts, whatever that happens to be a graph of. In this situation, its amount of water. It could be anything, right? There's different examples in the textbook that you can look at. What does the x-intercept represent? The x-intercept's that point right there, right? That was the y-intercept. The x-intercept is down there. I'm going to write x-intercept, but I'm also going to call it the horizontal intercept. X-intercept. Or you could call it the horizontal intercept. Or you could call it the t-intercept because that's the variable here, but you should get used to seeing all those things. Whoops. What does that one represent? Where's the point in this table that one represents? Which point is that? That one, right? What's the value of that horizontal intercept? The units for the vertical intercept were liters, right? This was 4 liters. What are the units for the horizontal intercept? Is it liters? Is it 8 liters? Not liters, is it? What does the 8 represent? Minutes. It's time, right? Since it's a horizontal intercept, it's on the horizontal axis. It's the units of the horizontal thing, minutes. What does that represent? What does 8 minutes represent in this situation? What does 8 minutes represent? It's time that it took for what to happen? The whole thing to drain, right? This is the time it took for the whole thing to drain. You might say it's the amount of water at the end, but in this situation, I don't want to put the word end here because sometimes things don't end there, they keep going. I'm going to put time when amount of water became 0. Of course, in this case, that means the time it took for the whole thing to drain. But the key here is this. Okay? The key here is this. This Y-intercept is the amount of water, the vertical value when the time is equal to 0. This thing is the time when the amount of water became 0. Okay? It has to do with 0. Look up in the table here. The Y-intercept is the value when x is 0. The x-intercept is the value when y is 0. Okay? The 2 intercepts there. So there's not really space here, but I'm gonna put that down here. Y-intercept and x-intercept. Let's get rid of this graph because we don't need it. In general, the y-intercept is the starting value or initial value. Or initial value. Or more importantly, it's y value when x is 0. Y value when x equals 0. The x-intercept is the opposite there. I don't want to put the ending value because you don't always have an x-intercept. The y-intercept is going to be more important to us than the x-intercept. That graph, we had both intercepts. We had a y-intercept and an x-intercept. What about the previous graph? There was a y-intercept here. Was there an x-intercept? Was there an x-intercept? There wasn't, right? Because this just kept going up and kept increasing. If you wanted to have an x-intercept, you'd have to actually go back in time, if it's filling up at a certain rate, but that's not possible in our situation, right? So there isn't really a meaningful x-intercept in that situation. The y-intercept is always going to be important to us because it's going to be the starting value, wherever the graph starts. But you can get either one of them just by recognizing that it's where the other one is 0. Y-intercept's where x is 0. X-intercept is the x value where y is 0. Or when y is 0. You could put here, if you want, that it might be the ending value. If we're going to write an equation for this, we're going to write the equation based on those 2 situations. Okay? So once you've written that, I'll go back to those 2 graphs. Okay, so let's look at each of these graphs here. You might not have space. I'm going to write up in the space up here. Let's look at the first one. Here's how you get the amount of water. If you wanted the amount of water after a certain number of minutes, let's say you wanted the amount of water after 3 minutes, right here. So let's say you wanted the amount of water here, this amount of water. You wanted to know how much it was. You could look in the table, of course. But you could calculate it by saying, I'm starting with 1, and how many times would you have added on this much. How many 1.5s would you have added on? How many jumps do you make on the graph? You go 1, 2, 3, right? 3 times you've added on 1.5. 3 times 1.5. That's if you're writing it as, that's if you're trying to find after 3 minutes. After 10 minutes, how would you figure it out? You don't have the graph, doesn't go up to 10 minutes, but how would you work it out? After 3 minutes. I should really use more space than this. After 10 minutes, what would it be? After 10 minutes. How could you work it out? How much water would you have? You start with 1, and how many times have you added 1.5? 10 times. 10 times 1.5. If you want to write an equation for this, all you have to do is make this the variable. Okay? Your equation is going to be 1 plus whatever this is. T is the variable here, right? T for time. T times 1.5. That's your equation. Except for the way that people write it is they don't usually put the variable first here. If they want to say 1.5 times t, they don't say t bracket 1.5. What do they say usually? Or what do they write? What do they write? Instead of t times 1.5 like that, they write it like this, 1.5 t. This is the equation for that line. Okay? And for some reason, when you see it written, often they put this term first. They go 1.5 t plus 1. Although I think it makes more sense to write it the way I have in green there. Because this is your starting value. And that's the change for the amount of water that's increasing. But when you look on your formula sheet or in the textbook, this is the way it's written with there's 2 terms in there, and they write the term with the t in it or the x in it first. That is called slope-intercept form, okay? Because this is the slope. That's the y-intercept. Okay, if you want to write the equation of a line, if you know the slope and the y-intercept, you can write it. For the second equation, you can write an equation for that using an a and a t here. If we just put in the slope here and the y-intercept here. In this case, the slope is negative, right? What's the slope? It's negative 0.5. The equation for this is going to be negative 0.5t plus 4. Or I think it's better to write it as 4 minus 0.5t. Either one of those ways is fine as an equation for that line. If you want to know the value at any point, you just substitute in a number there for t. Okay? If you want to know a value anywhere there, you substitute a value in for t. If you want to know the value here, and you don't have the graph, you can put in a 5 in for t there, and then just work out what a has to be. Okay? In general, maybe somewhere for yourself. Somewhere for yourself, this is this form, slope-intercept form. Slope-intercept form. Slope-intercept form is y equals, I would say it's ax plus b, where a is the slope and b is the y-intercept. They use those letters. Sometimes you might see people write it as mx plus b. I have no idea why they use m for the slope sometimes. Doesn't matter. If it's some number times x plus some other number, slope, and that's the y-intercept. Okay, slope-intercept form. Okay, you can write this if you know those two things. If you know the slope and you know the y-intercept, right? That form is on your formula sheet that you get on the provincial exam. It'll say this. Okay? If you look at the back of the room on the top wall by the clock there, that's just an enlarged version of something that's on the formula sheet. See those three different versions there? Okay, it says the equation of a line y equals mx plus b. On the formula sheet they use an m, but it doesn't matter what letters you use. Okay, the examples that are there in that section from the textbook, let's have a look at them together. We're not going to do them all. But you notice it gives you a picture, and it asks you, first of all, it asks you what is the slope, what's the y-intercept, and then write the equation. If you can figure out what the slope is and what the y-intercept is, all you have to do for the equation is write y equals, leave a space, and leave another space, right? And you put those two things in there. This is the slope. Okay, that thing right there. You fill in the slope here, and then you know the y-intercept. You fill in the y-intercept there. Okay. The y-intercept you don't really have to work out. You can see what it is. What's the y-intercept here? Y-intercept is right there. What's the y-intercept? 1, right? That means your equation is going to have a 1 there. What's the slope here? How can you find the slope? If you don't have 2 points to use for your slope, how do you find the slope? Well, you need to use some points here. You could use that point. You can use those 2 points if you want. You can use any 2 points. If you notice that it goes 3 squares across and 2 down, as long as you look at the scale, that represents 3 on the scale. From there up to there is 3, and from there down to there is minus 2. So the slope is minus 2 over 3. Change in y over change in x. That means you just put negative 2/3 here. The equation of that line is y equals negative 2/3 x plus 1. This equation represents that line. If you wanted to know, any other point on the line, like this point, you could put in a 3 for x and work it out. You can substitute in a point, or substitute in a value here, and find this value. But that's what you're going to have to do later on in this section. The other two, there's another question for you to try there. There's another question here about how to rearrange. It says rewrite this equation in slope-intercept form. We can do this one together, at least the first part. If you're trying to put that into slope-intercept form, basically you can work with some of the algebra you already know, right? Just write that down as is. But if you're going to change it to slope-intercept form, what you want in the end is you want y by itself. Basically, to put it in slope-intercept form is isolate y. Okay? Slope-intercept form has y all by itself on one side. How could you start isolating y in this equation? There's probably more than one step you could tell me is the first step. Because all the terms are on one side and there's a 0 on the other side. We want to move this so that it says y equals something. We got a couple choices here. Well, this is the y term here, right? So you could move the other things to the other side and leave the y term on this side, or what's your other choice? You could move those two terms over. Or it doesn't matter which side you get the y on. Couldn't you move this term to the other side? What happens if you move that y term to the other side? If you move this term to the other side, you can move terms on an equation from one side to the other, right? If you move this to the other side, what happens when it gets to the other side? It becomes positive, right? 2y is what's left on the other side if you move that? 3x and minus 600. That's probably the easiest thing to do first, is move that term to the other side, since it's negative. I'm going to put down here, move the y term since it's negative. What do I do now if I want to get the y by itself? If I want to get y by itself and it says 2y, what do I do there? Divide by. If I divide by 2, I got to divide each of the other terms by 2. This leaves me with just y over here. This thing you can just leave as 3 over 2, or you can write 1.5 y, or x, whatever you like. But you can leave it as a fraction if you want. You can write it as 3/2 x, whatever you like. 1.5 or 3/2. What about this though? 600 divided by 2 gives me 300. That's what that is. That's the equation. And if you are the kind of person who's uncomfortable having the y on the right side, anybody one of those kind of people? Uncomfortable with the y on the right side? You don't like writing your equations in grade 8 like this, your x equals that way, backwards? You may well be one of those people. You can write it the other way, okay? And say this.